Okay, so if we're going to do, notice what's different here. We've got a weak acid and a strong base. We've got a weak acid and a strong base. So it's going to be a little bit different. We're not going to have exactly the same thing. So if I take pretty much what I had before in my weak acid and my strong base, and this time let's react, here's our strong acid, we had HClO4, let me get to the right slide here. If I've got a weak acid, so we're going to do 0.1 molar acetic acid with KOH. So that's what we're going to react. I'm going to go to a blank slide here, and we're just going to react it like we did before. But I want you to see what is very, 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 very different here. If I'm reacting acetic acid, so let's go ahead, we'll still put 100 milliliters of 0.1 molar acetic acid in our container. We're going to react it with KOH. Of course, it's going to make potassium acetate and water. How do we find the initial pH? Just negative log of 0.1?
No.
No, can't do it like that. It's a little bit different, right? Yes. So before we start, we've got, all we have is CH3COOH, which in solution is ionized into H plus and CH3COO minus. If I have 0.1 molar of this, how much breaks apart? X. I make X, X. You know this, you've done this. 0.1 minus X. I write my Ka expression, H plus times CH3COO minus over CH3COOH. There we go. I plug in 1.8. I looked that Ka up in the back of the book. X times X over 0.1. Remember, approximately equals 0.1. So I've got 0.1 there. So X equals 1.8 times 10 to the negative fifth times 0.1, and take the square root. So I got X equals 1.34 times 10 to the negative third. How do I use that to find my pH? That's right, that is my hydrogen ion concentration. So pH equals negative log of the hydrogen ion concentration. So that's going to equal 2.87. What do you notice, even right off the bat, what do you notice about the initial pH of this weak acid versus the strong acid? It's higher. It's not as acidic. Does that make sense? Yeah, sure, because 100% of the strong acid broke apart. Only a small percentage of this breaks apart. So yeah, sure, it makes sense that it starts out with a higher pH. Yes, Meg?
Is this the same amount of acetic acid breaking apart each time? Like, does it change?
Ooh, well, let's try to answer that question by continuing on, okay? So let's try to answer that question by continuing on. So now let's add some KOH and let's see what happens here. So that's how we do it before we add any. We got that whole Ka expression, and we found that initial pH, and we can put that on our graph and so on. So now let's add, I don't know, what, about 20 milliliters or so? Okay, 20 milliliters or so. That'll work. 20 milliliters of 0.1 molar KOH. I can do an ICE chart. I want to do it in what kind of units? Millimoles. So how many millimoles of acetic acid? 10 millimoles of this. How many millimoles of this? 20? 2 millimoles of this. How much reacts? 2 completion. So minus 2 plus 2. Now, before I never really filled out the product side. Here I am. Why? It's a buffer solution. Exactly. It is a buffer solution. We made a buffer solution. So if you look, what do we have? This is a what?
It's an acid.
Weak acid. And KCH3COO is its conjugate base. Weak acid conjugate base. We made a buffer solution. Actually, we should say yay, because we've got this really cool equation that we love that helps us to figure out the pH of the buffer solution. pH equals pKa plus log of A minus over HA. So how do we find the pH of this? It's really pretty
Just
easy. Plug it in. pH equals pKa, so that's negative log of the Ka for acetic acid, 1.8 times 10 to the negative fifth, plus log of, what's my A minus concentration?
over 100.
Okay, since we're doing a ratio, can we leave it in millimoles?
Yes.
Yes, because this is going to be 2 divided by 120. This is going to be 8 divided by 120. So it's over 120 over 120. It's not going to make any difference. So all I have to do is plug in 2 over 8. So then solve. So 2 over 8. Take the log of that plus negative log of 1.8 times 10 to the negative 4, and I think you get 4.14. 4.14. Now, we started, what was our initial pH, like 2 something?
2.78.
2.78. Now, is this a bigger jump than before? Yeah, that's definitely a bigger jump, but did it jump all the way to what you think it might end up being at the equivalence point? No, it didn't jump there, but it is a bigger jump than before. You know, before we had this, and this is what we're going to do in lab, is compare these two curves. Before we had this barely increasing, and then woo, suddenly increasing curve. Here, we're starting at a higher pH, and it's going to almost curve up like this. Yes, there's not going to be a huge jump in pH as we add the base, but it's going to be a buffered solution. There is a greater difference in pH. So let's say we added 90 milliliters of KOH. If we added 90 milliliters of KOH, we still have a what? You still have a buffered solution. If I change this to 90, that changes this to 9, changes this to 9, changes this to 9. Sorry I didn't erase it, but changes that to 9. I'd be left with how much here? 1. This would be 9, and into my thing, instead of having 2 over 8, I'd have 9 over 1. It's always salt over acid. So 9 over 1, just to compare here, let's see what that gives us. 9 over 1 plus log of that. That equals, so when it's 9 over 1, it equals 5.69. So did the pH go up? Yeah, the pH definitely went up by more than we saw in the strong acid, strong base. Are we at our equivalence point? No. Because the equivalence point is going to be when these two numbers right here that are 1 and 0, when those two numbers get down to 0. Okay, so that's where we're going to have to start tomorrow, is with the equivalence point, what happens. Because at the equivalence point, all we have is salt. Who remembers from the last test, how do you determine the pH of a salt? Hydrolysis.
KB, KW.
Yes, so that's where we're going to go tomorrow, is with hydrolysis. So that